All 18 views are you.
18.
What part do you keep thinking?
Just looking straight. It's not. Wait, okay. What's this part here? Just like as beautiful beauty.
There's so many notes.
Oh. Yeah, that's my God.
The guy in the back fell.
Yeah.
No, it's fine. If you have an injured foot.
Okay, welcome to Lab 12. So this lab we will build on the statistics that we're learning in the lectures, and we'll go over Monte Carlo simulation. And Monte Carlo simulation is a technique where you're able to use randomly generated points to simulate things. And in this case, we're going to look at how can we use simulations to find areas of geometric objects and then solving integrals. If I can, it's to work. Okay, so in this problem, we're going to find the area of circle. Suppose if we don't know the area of the circle, which is a is equal to pi r squared. If we don't know that, how can we find the area? So let's say we have a circle and it's a unit circle of radius r is equal to 1. And I place it in the x and y coordinate where the center is the origin. And because it has a radius of 1, let's see. So here it should be -1. Here should be 1 in the x coordinate. And then in the y-axis, I also have -1 and 1 in the y coordinate. The Monte Carlo simulation for finding the area goes like this. If I were to draw a square that fully captures the circle, like this. And we already know the area of the square. And in this case, this is 1, so it's 2 times 2, which is equal to 4. And we can get is the area of circle is equal to the area of square multiplied by area of circle divided by area of square. So mathematically, these are equivalent because you can cancel these out. But what this says is that since we already know the area of square, and then what we can view this as is the ratio between the area of circle and area of square. And the simulation goes here. It says that if I generate points from a uniform distribution, that means that it has equal probability of being anywhere. So if I generate points within this square, and it has equal probability of lying anywhere. So for example, here, 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 it has equal probability every time it generates. Then the number of points that lies within the circle should be proportional. So number inside the circle should be proportional to the area of the circle. And the number of points that is outside of circle should be proportional to the area outside of the circle. And similarly, the number of points in the square should be proportional to the area of square. And the proportionality should be the same. And therefore, since we have the area of circle divided by the area of square, we can replace these as the number of points that are within the circle divided by the number of points within the square. And the number of points within the square is just the total number of points. And in this case, we'll call this total number of points n. So for example, if we have n equals to 10, we will randomly generate 10 points. And these points have equal probability of being within and without anywhere inside the square. And so we'll generate 10 points and we'll count up how many points are within the circle and how many points are outside of the circle. And the end result should approximate the area of the circle.
How do you know if they're in the circle?
Great question. So the first step is to generate points. And the second step, as you mentioned, would be to determine whether or not if they're inside or outside the circle. So in these cases, we don't know the area of the circle, but we do know the equation for this circle. So the equation of the circle is x squared plus y squared is r squared, and r is equal to 1 in this case. And we can derive this from the distance formula. Because we're centered at 0, 0, anything that's distance 1 should be on the circle. And the distance is square root of x squared plus y squared. And that should be equal to the radius. And therefore, the circle's formula will be this. And so this equation is an equation for line, but we are interested in the area inside circle. So anything that is smaller than 1 is inside the circle. So if the points, say any of these points have coordinate x of I and y of I, then if they satisfy that x of I squared plus y of I squared is smaller or equal to 1, they're inside the square, inside the circle. Else it's outside the circle. So this will be the equation that we'll use to get the condition of whether or not it's inside or outside the circle. So now we have our total n that we will assign and the number of circles that will count using this condition. We should be able to solve the area of the circle. Okay, so let's try that in Python. So we have number of points, which I define as n. Let's say in this case, it's letting us to generate 5,000 points. So n is equal to 5,000. And the Monte Carlo simulation says that you can generate x and y coordinates using uniform distributions. And that in Python is np.random.uniform. And if you search this in Google, you'll see how can you use this. So the first argument is the lower bound, and the second argument is the upper bound. And the size is the number of points that it will generate. And because in our case, we want the x coordinate to be within -1 and 1, so the arguments should be -1 and 1, and the size will be 5,000. So in that, I'll give -1 to 1 with 5,000 points, which is n. And you can verify this. Oh, I need to import NumPy. That it's generating points that are within the range -1, 1, and the shape should be 5,000. And similarly, we'll do the same with the y coordinate. the y-coordinate is also from -1 to 1. So we'll generate from a uniform distribution using random uniform from -1 to 1 with endpoints. So let's visualize these points. What should we expect? We should expect that these points are randomly distributed within the square. So we plot these. We see that indeed it's all over the square. I'll set the aspect ratio to 1 so that it's indeed a square, it's not a rectangle. Okay. But what we care about is what are the points that are within the circle and what are outside. So we just need the number of points that are within the circle. So what we can do is to use the condition of the circle's formula, which is x squared plus y squared is smaller or equal to 1. And so anything that's x squared plus y squared, for each of those points we can calculate. And if it is smaller or equal to 1, this is within the circle. And you will give true or false for these statements. So in circle. So this is the condition for points within the circle. And using this condition, we can plot the points that are within the circle, let's say using blue points. So I will index these x and y using the condition in circle, because in circle is true or false, so it will get all the points that are true. And I'll label this in circle. So these are the points that are within the circle. And I will also plot the points that are not inside the circle. So we saw that in circle is an array of true or false. And when we operate true or false, we can have a not argument. So if we use this curly symbol, it will become false. So it reverts true to false and false to true. So anything that is not inside the circle, I'll label it outside of circle. And change the color to red. So anything that's red is outside of the circle. And I can give it a legend and place it outside to anchor. Okay, so we are able to visualize the points that are within the circle and outside the circle. And let's give them some transparency so overlapping points can show up. Okay. So that these are the points that are within the circle and these are the points outside the circle. And we can count the number of points that are inside the circle by summing up the true or false statements. Because in Python, true is equal to 1 and false is equal to 0. If we sum them up, we get the number of points. And the number of points is around 3,000 in this case. So num points in circle is this. And so the area of circle, the approximate area we calculated is 4 times the number of points inside the circle divided by the number of total points. So that will be 4 times the number of points inside the circle, which is around 4,000, divided by the total number of points n, which is 5,000. And the area of the circle that it estimates is around 3.167, which is pretty close to the truth pi, 3.14. So let's label this axes, set x label as x, set y label as y, and then set the title as the approximation. So area is equal to area of circle. Okay, so and this is the full cycle for Monte Carlo simulation. Any question? So the main part is actually just generating random points from uniform distribution. And other things are to impose the condition and to calculate the area according to our derivation. And we have visualized the points that we have uniformly generated that are inside and outside the circle. And for your practice problem, you will do this same thing, but with different number of points, so different n. So in our case, we used 5,000, but for your practice problem, you'll use 10, 100, 1,000, etc., up to 10 to the 6. So the simplest thing we can do is to just change n. It's 10. So we can look at the area for 10, 1e6. Okay, n needs to be an integer. So n, because 1e6 is a float, but this needs to be an integer. So you want to convert it to integer. And then you can generate a lot of points. Yeah.
To be an array of all the powers, how do we turn that into an integer? Is it possible?
So yes, but it will be a little advanced. So one thing you can do is to write this in your for loop. So every time you have for n in n list, the first line you convert this to an integer. Or as you suggested, if you have log space from 1 to 6, 6 numbers, and list. So now they are all float. In order to convert them to integer, you can use as type integer. So n list is equal to np list as type integer, and they should become integer. And these are advanced NumPy syntax. Or alternatively, you can use n is equal to integer of n inside of the for loop. So you could do this by changing n, but of course you don't want to do that. So you want to write a list and use for loop, and that will be your practice problem. And I also changed the random seed. Oh, one thing I forgot to mention is that because we are generating random numbers, every time I run this code, it will give us different numbers for y, x and y. So for example, now it's minus 4.3. If I run it again, it becomes minus 6.0. So for reproducibility, so that we generate the same number, there is a function called seed. So np.random.seed. And the seed takes in an integer. So you can type in any number, but in this case, I think it wants a random seed of 0. This seed will tell the random number generator that we are going to generate the pseudo random number in a specific way, such that on different computers, it generates the same result. So that if I put this in the same cell as the uniform distribution, every time I run this, it returns the same result. If I don't put this, every time it generates different result. So for reproducibility in this lab, we'll use random seeds. And in your practice problem, you're seeding the random number generator with a seed of 10. Okay, we'll come back in 10 minutes. Okay, so when you do n as type, you need to assign n equals to n as type. Yeah, I think that will. So for I in n, so n list. So this n is a list, right? And the I will be the individual n. So you don't need to index those.
Oh, yeah. Okay.
You can't put in n, you need to put in I. So n is the list.
Thanks for I and stuff.
Not callable. Oh, square area is a number. So I think you're multiplying it. So star.
Okay. Yeah.
Then you can check your visualization with this. I don't know. Oh, because n is 10, 100,
Okay.
and the I will be 10, 100. But you want the I to be 0, 1, 2, 3,
Yes.
5. So what you can do is to do,
Can I try saying range? I tried saying I in range of n
yeah,
and erase an error.
to do that, you need to do for I in range length of n,
Oh,
right? Or you can also do enumerate, but either way works. Mhm. Oh, because you got log space 1, 6, 7, so you have 7 points.
Oh, is it not like the last one isn't included?
Last one is
Oh,
included.
okay.
So if you print it out, it died.
Okay, I'll restart it. Okay, thank you.
The fact that she's not looking at the picture, and then she told me that he knew that.
So here I'll go to time and circle. Like area on the circle, solve your area on the circle. So one, two,
It's
three.
It's
Were you doing fine with this question? So for the practice problem, I won't code up everything again, because the main thing is just do the simulation, just 2 lines, and then check the condition and then calculate area. So what I will do is to show you how to copy and paste. And that's a very important skill. So say we have this code that already works for n is equal to 5,000. But some of the conditions are different. So the radius of the circle is 2, so we want to change this 1 to 2. And we also want to change the random seed to 10. So instead of 0, I change it to 10. Okay, and that should be still runnable. Okay, well, what we want to change is to have different number of points. So we want 10 to the first to 10 to the 6th. We can use np.log space from exponent 1 to exponent 6 with 6 points. And that should generate 10, 100, 1,000, etc. And we want to make it an integer. So as type integer. And I'll assign this as n list. And then so I will write a for loop to put all of these inside the for loop. So for n in n list, I put everything in. So I'll combine these. I don't need to print the area or the error, so I remove those. And I put the plots inside the for loop too. Okay. And I will remove the n equals to 5,000 because now n is defined in n list. So if I run this code should generate 6 figures because inside the for loop, we are generating figures. So you'll see 1, 2, 3, 4, 5, 6. So one of the things you might have noticed is that the error is really big. That's consistently big for all of those. That's because we need to change the ground truth. In this case, we're looking at circle with radius 2. So instead of pi, it should be pi times r squared. And that should be circle radius squared. And if we do that again, the error should be correct. And as n increases, the error decreases. But the question is asking us not to plot 6 figures, but in one figure with different subplots. So what you should do is to move this figure axis command outside of the for loop. And you generate 1 times 6 axes. And the figure size, of course, you need to change to avoid squishing. So it will be 5 times 6, 5. And then because you change the axes, you need to make the x, change the x to axes of I. And where I is the index. But in the for loop we used for n in n list, we don't have I. So a way to solve this is to use enumerate. So for example, if we use enumerate, let's print I and n. What it does is that the first argument will be the iteration index. And the second argument is the element within the n list. So if you print n list of I, it's the same as the n. So this is the enumerate command. So I can use for I and n in enumerate and list to use to loop this through. And it will take a while to run, but this gives the same result. And you can hide the legend because we already know what's inside and what's outside. And at the end, you can put a plt.type layout to space the figures out. Other than that, this code is already working, but if you want to optimize this code, you can put things that are not changing with the iteration. For example, these constants, you can move this outside of the for loop because they're not changing. But you don't need to because the code is working and you're not a software engineer. So this is the final result. So what can we see from these results? Is that when n is very small, we weren't able to sample the full area of the circle, and therefore the area error, estimation error, is very large. As n increases, we were able to sample the majority of the area, and therefore the error decreases as n increases. When n is extremely large, the error becomes very, very low. And to quantify this, let's look at the error dependency on the number of points used in the simulation. So in this problem, we want to find the area of the unit circle using the simulation. Now, it's not using 5,000 points or just 6 different number of points. We want to use 2,000 points that are between 10 and 10 to the 6. So if we look at the shape, there will be 2,000 points. And using a random seed of 0 and calculate the absolute error. So what we can do is from the practice problem, because the practice problem already, we know we already written a for loop. But this time, the for loop, we're not looping through n list that's only 6 points, but we're looping through n list that is 2,000 points. I think it's here. And we don't need to plot the individual cases, so I will remove the plotting commands. Okay, and then change the things because we're looking at the unit circle, the radius should be 1, and the random seed should be 0. So what this does is that it does the Monte Carlo simulation for 2,000 times and stores the result for different ends. So if we run this, this should take some second to run. It should generate a list of circle areas and a list of errors. And we want to plot the estimated area versus the number of points. So that will be fig x is subplots for n list versus the circle area. Oh, subplot should be x dot plot. Okay. And because on the x-axis, so let's do set x label as n and set y label as the circle area. Because we're sampling different numbers of n on a logarithmic scale, it doesn't make sense for us to plot in a linear range. So what we can do is to set the x-axis as a log axis. To do that, we want to change the plot to semi-log x. So that will change your x-axis to a log axis, like this. And let us also plot a horizontal line on pi, which is the ground truth. So we can just say ground truth. Set the color as red, line width as 1, and then line style as -9. Ground truth. Okay. So what we observe is that when n is very small, it cannot sample all the areas. So the area of estimation is fluctuating a lot. But as n increases, the circle's estimation area, estimated circle area converges to pi. We can also look at the errors. So let's plot the error list. Okay, and let's also change label. In this case, let's also make the y-axis also log. So using log command, x and y axes are all log. And I will give it some transparency, say 0.04. So this is the graph for error versus number of points. So as the number of points increases, the error decreases. And because it's on a log plot, the relationship is linear. So the error linearly decreases with respect to the number of points. And so you can try this out with your practice problem. And in this case, you're looking at the radius 2 with a different number random seed. But you should be able to observe the same result. Okay, we'll come back in 10 minutes.
So she just.
Yes.
This is our test. This is our seats.
And then I get another, okay, I think the arrow seed is two. Yeah.
But n, the variable n isn't there. So you can input.
Okay, arbitrary, just whatever, okay,
But in the efficiency,
but it can be like.
to be written network, the range can be over that the error.
Okay.
Because it gives you the whole area. You are covered with very small.
Okay, yeah.
Down to the fact, but where do you use it?
That's true. So maybe we should put this in, to be honest. It's everything.
Okay, for this practice problem, we already have sample code from the guided practice. So we can just copy the code and then change the radius to 2. And then check if the ground truth is correct. So that's pi r squared. And then the random seed is 10. And the number of n's is correct too. So we can run this code. And this code suggests that when n is small, again, it's fluctuating because it hasn't sampled all the area of the circle. But as n increases, the estimated area converges to 4 pi. And the error, absolute error, decreases as n decreases linearly. And the third plot conveys the same information as the second plot, but it's based on density. So you can see the density of points is the highest along the diagonal linear line. So these points are outlier points during the random distribution. So when you randomly generate points, you can sometimes achieve a lower error just by random chance. And because of that, we can explore the effect of randomness with sampling. So currently we're looking at the number of points used for simulations. So let's fix that to 5,000. But previously we only run this simulation for one time. So what will happen if we run the simulation multiple times with different number of random seeds? So this question asks if we fix the number of points within the simulation to 5,000, but we run the simulation independently 1,000 times, what will be the average estimation using Monte Carlo simulation? So what we want to do is first finding the area with 5,000 points is similar to what we have just coded. So I think in the first question, so I'll copy the code from the first question. Okay. So this is the code from the first question, and it generates the area of the circle when we use n is equal to 5,000. But now we're interested in when we change a random seed, when it's not only 0, but it's from 0 to 999. So that will be NP arrange from 0 to 1,000 with a difference of 1. That will be generating from 0 to 999. So that will be the seed list. So now we need to write a for loop. So for I seed in enumerate seed list, n is always the same, so I can put this outside the for loop. And I will give a different number random seed as seed. And the circle radius, these are all constant, so I'll move that outside. And I want to store the result of the circle area. So I'll give it a empty list. So I will append the result to that list. every time. And then at the end, I will cast that list to an array. So after I run this, it generates different number of guesses, and I can look at these numbers. So let's plot this big X. So if I use axes, plot these numbers, you see that they fluctuate quite a bit, but they are centered around our final guess of the ground truth of pi. And if you want to look at the distribution, you can plot it with a histogram, and the command is x.hist. And this is the histogram. In the histogram, you can also plot the vertical line, x, v line of the ground truth, which is pi. Give it a color, give it a line width, and then give it a line style. Oh, the ground truth in this case wasn't defined. So ground truth is np dot pi times radius squared. So here is the ground truth. And let's also look at the mean of the 1,000 simulations. And the mean is the black line. You see that the mean of these simulations are close to the ground truth. So even though each individual time, sometimes I'll sample 3.1, sometimes I'll sample 3.2, but when I sample a lot of points, on average, the simulation's average will be equal to the ground truth. I think I have a more advanced plotting method that makes the plot look nicer, but they're basically the same. And so using these code, let's explore if you are looking at 10 points, 100 points, etc., up to 10 to the 6 points, and ignore the 5,000 points here. And then plot the histogram to see if the mean will be the same. And this should be your final result. We'll come back in 10 minutes. So this basically is another for loop by changing the seed. Okay, seed. Okay, how are we doing on the practice? So given the guided practice problem, we're looking at different sampling at 5,000 points. So we can copy the code. And then instead of using 5,000 points, in this case, we're looking at different number of points. So that's NP log space from 1 to 6 points as type integer. And this will be our n list. And instead of defining n, we'll use for I and n in enumerate n list. And everything below, we make a for loop. So if you run this, this will generate 6 figures, and each figure will be a different histogram. And of course, we haven't changed the radius. So the radius should be 2, and the random seed are different numbers because they're using sampling. And this will take a while to run because it is generating a lot of different numbers. And because we want to put them on the same figure, we will make the figx command outside. And then we have 6 different subplots and change the dimension. And instead of axes, we use axes. And then change to axes of I. And the result should be 6 histograms. And it'll take a while to run. As n increases, the histogram becomes more and more like a normal distribution. When n is equal to 10, you see that the histogram is more discrete. And the reason is that there's only 10 different combinations of the ratio, and therefore only 10 different areas possible to sample. But then n increases, it becomes more and more continuous. And another observation is that the red and blue lines, dashed lines, each representing the ground truth and the mean of the sampling, and they're very close to each other for different ends. Meaning that even though when we're sampling, we could sometimes get off targets, so around 12 or around 13, but on average, it should be very similar to the ground truth, which is 4 pi. Okay, so you might be wondering, why are we solving the area of circles? We already know the area of circle is pi r squared. It's because this is kind of a toy example that we start with Monte Carlo simulation, and we can solve areas under a curve or integrals of complicated functions. So these functions, we definitely don't want to solve by hand, but we can solve with Monte Carlo simulation. So let's take this as an example. So in this case, we want to integrate from 0 to 1 of this function f of x. So f lambda of x is 2 times np sine of x times tangent of x squared times e to the minus x squared minus 0.1. And what we want to do is to integrate this function from 0 to 1. So let's first plot what it looks. So let's define x points. And we are interested from 0 to 1. So from 0 to 1, I plot 1,000 points. And the y points will be when I evaluate f at different x points. So I plot the x points and y points. And this is the function. And let's also plot a horizontal line of 0 because we're taking the integral, and the integral only cares about the area with respect to y is equal to 0. Okay. And from the geometric interpretation of integral, any area that is above 0 and under the curve are positive areas. So this area is positive. And any area that's below y is equal to 0, but above the curve is considered negative. So this is negative area. And the net area, so the positive area minus the negative area, will be the integral. So what we can do is to use a Monte Carlo simulation to bound this curve, and then anything that's within it, we can consider as area. So instead of using a circle, we're looking at areas that are bound by y is equal to 0 and this curve. Okay, and to do that, let's first define the bounds. In this case, we want rectangular with some x minimum and rectangle of some x maximum. And the x minimum we can set to 0 and maximum set to 1 because the integration ranges from 0 to 1. And now set the x limit to rectangle x minimum and x maximum. And I will also set the y limit as the rectangle y minimum and y maximum. And we'll need to define those variables. We need to define these y minimum and maximum such that we can capture all these areas. So let's say we can do y minimum of minus 0.05. Okay, that's within the range. And the maximum should be not 1 because it doesn't capture the area. So let's say 2. So now these areas are within the range of this bounding box, which is the rectangle. So we can calculate the area of the rectangle. That should be equal to rectangle's x length times rectangle's y length. And the x length should be equal to x maximum minus x minimum. And similarly, the y length should be y maximum minus y minimum. So in this case, we define the rectangle's area as y rectangle is 2.5. So the total area here is 2.5. So within the boundary of the rectangle, I want to sample x and y from a uniform distribution. So random.uniform. And for x, I want to sample from x minimum to x maximum with 5,000 points. Okay, so n is equal to 5,000. And similarly, we sample y points from a uniform distribution from rectangle's y minimum to y maximum with 5,000 points. So this is the simulation. And now we need a condition for positive area, which is the area under the curve. So let's first plot x and y points. So x and y. So you see that it's all sampled. So if we put the alpha as 0.1. Oh, yeah, so all of the areas are being sampled. So if we do 500 points, maybe. So this gives a more clear view of this rectangle as being sampled. Okay. And the condition for area under the curve is that when the y value is smaller than f of x, but it also has to satisfy that it's greater than 0. So, and y is greater than 0. So when these conditions, both of these conditions are satisfied, it is under the curve. So this is the condition for positive area. And we can plot these by selecting the points that are under the curve and give it a, let's say, blue points. So you see that this area, this curve, is being identified as area under the curve. So this is a positive area. And next we want to look at the condition for negative area, which is the area above the curve. So for this negative area, what it has to satisfy is that y needs to be greater than f of x, but smaller than 0. So above curve, our y is bigger than y of x, and y is smaller than 0. And again, we can plot the points at which it's above the curve in red. So these red points represents those that are above the curve. Let's see, we have 5,000 points. And if I only plot the ones that we are interested in, so this is the positive area, and this is the negative area. So we are able to use the conditions to identify those points, and now we can calculate the area. So the positive area, or the area under the curve, is the rectangle's area times the number of points that are under the curve, np.sum under the curve, divided by the total number of points, which is n. And the area that is above the curve is the rectangle's area times the sum of the condition that's above the curve, divided by. And the net area, which is the final result of the integral, will be the area under the curve minus the area that's above the curve. And in this case, we got the result of 0.296. You can verify this in decimals. So in decimals, to integrate, you can type int from 0 to 1 of some function f of x dx. And you need to define the function f. And in our case, f is equal to 2 times sine of x times tangent of x squared times e to the minus x squared. I think it's minus 0.1. And so this is the ground truth according to decimals, 0.262. And so the absolute error is equal to the absolute value of the net area we calculated minus the ground truth. So the net absolute error is around 0.03, which is pretty good. And we should be able to increase the number of n in order to decrease the error. And now the error is 0.03. And you see that more of the points are sampling the area that we're interested in. So you can increase the number of points to decrease the error. Okay, any question? Okay, you can use the similar code that we used in this case. Okay, so positive area, negative area, to find another integral with different bounds. So that's everything for this lab, and stay around till 2.
What's the answer script?
Like this. And the result of your integral should be matching that from the Desmos.